I made my way from academia to industry now. So this paper is about main parts of my PhD thesis, and it's about new side channels for breaking SSL and TLS implementations. And this is very specific to each implementation. This is a joint work with my colleagues, Juraj Somorovsky, Eugen Weiss, Jörg Schwenk, Sebastian Schinzel, and Erik Tews. At first, let's have a look at TLS. TLS is some kind of intelligent glass, because privacy and confidentiality matters. Sometimes you can see that something's going on, but you don't see what. So you have some encrypted garbage, which you really like to decrypt. Okay, in this case, you will probably hear what's going on. Okay, so getting back some years, 1989, first Oracle attacks on TLS, something called Bleichenbacher attacks. I don't know if you're familiar with it. For those of you who are not, we will do a short recap. This is some little theory. It's necessary to understand the attack and how it works, and sorry about that. So what you need is an RSA-based key exchange in SSL, no DH, no DHE. You must have previously recorded your SSL TLS session of interest, which is encrypted, and you would like to decrypt it. And you need a connection to the target server, because you have to query the server with multiple messages. Okay, so short recap of Bleichenbacher's Oracle attack. You have an Oracle in the middle. You have an attacker here on the left, and the target server on the right side. So what you basically do is you have some kind of magically modified message. You send this message to an Oracle. The Oracle does some additional magic. It performs a TLS handshake with the server, and the server tries to fulfill the handshake. And what it does is it tries to decode the message, one message, particular message of the handshake. And if the structure of this message is okay, it continues with the handshake, and in the other case, it sends an error message. And by analyzing the response of the server, the Oracle can give the attacker a hint if the message structure was okay or was not okay. And when we have a look at the handshake protocol of TLS, there's one message that is of particular interest to us, and this is the client key exchange message, because it includes the little part with the fixed structure that we need to know if we hit the structure or if we found something completely different. The content is as follows. The structure is called PKCS number 5, version 1.5. You have a very fixed structure in case you apply schoolbook RSA to encrypt a message. The plain text is put into a structure, and if you're encrypting, not signing, then this message always starts with 00, 02, a padding, a random padding without the null byte, a single null byte as a delimiter, and this is what we would like to decrypt. This is the PreMasterSecret. You have 46 random bytes, and you have 0301, which is the TLS version, the current TLS version. And obviously, this is TLS 1.0. It's some kind of history, because SSL 3 uses 300, TLS 1.1 is 0302, and so on. And the whole message is encrypted with RSA, and put into the client key exchange message and sent to the server. And all we would like to get is this PreMasterSecret, these 48 bytes. Why are these bytes so sensitive? Because this is the only secret where the key material of an SSL session is derived from. So you have client random values, you have server random values, and The only thing, these ones you know from the client hello and server hello messages, and the only one that is input into the derivation process that is not known to an attacker is the PreMasterSecret. So you really would like to get this. And once you have it, you can compute the completely key block that is used to protect the SSL TLS session. So when you look at the structure, you can see that it's very fixed. So structure violations cause different response messages because the stack is no longer able to decrypt or to decode the message. And what Bleichenbacher did is exploit this fixed structure. So you send a message, you get a response, and with this response on, if you hit the structure, if it was correct, if you at least found 0002 right, you can narrow down an interval of possible values, and you do it again and again and again. You adjust the message, send it again, and you narrow down the interval until only one value is left. Now you can say, okay, you told me the whole message is encrypted, so how can I tamper it, and how can I play with it? Then, in this case, RSA comes to the rescue. We have the homomorphic property, and thanks to the previous speaker, I don't have to explain the RSA schoolbook encryption. And what it basically is you have a message 1 and a message 2, and if you multiply both encryptions, it's the same as if you had multiplied the messages and encrypted it. And why is that? It's simply because if you write it down, then you have m1 to the power of e multiplied by m2 to the power of e. You can put this in brackets and finally end up with this. All right. And what Bleichenbacher does is he thought about how can I exploit this. He simply has this value c, which is in this case our encrypted PreMasterSecret, and he chose some value s by random, encrypts this value, multiplies it with c, and doing it this way, you can interfere with the plain text message without even knowing it. Cool stuff, isn't it? Unfortunately, TLS 1.0 defines countermeasure. And the countermeasure is easy. If you find a structure that is violated, simply create a random PMS, and only in this case create a random PMS, and continue with this PMS. By doing it this way, an attacker has no idea if he simply chose a wrong PMS or if he hit the structure. He has there's no longer a side channel. All right, long introduction, but sorry, that was necessary to understand the attacks. Now we were looking for new side channels because of these countermeasures. Bleichenbacher couldn't be applied any longer. So what can we do? We can try to force different error messages by exploiting bugs in the implementation. And it worked for Java. Java JSSE, the Java Secure Socket extensions, contained a bug that did some magic in XORing two different arrays. And you can't spot the error from here because you don't know that there are no length checks on all these arrays. So if you manage to get these arrays to be of a different size, you will end up in an array index out of bound exception. And this in turn causes the TLS tag to send different error messages. In the one case, when there is this exception, you get an internal error, and in the normal case, when you simply didn't hit the PMS, then you get a handshake failure. So you circumvented the complete countermeasure by exploiting a bug. What they did was some kind of, let's call it coding by assumption, which you really should avoid. They simply thought, okay, there's no way that these arrays can be of different size, and yeah, that took down the whole implementation. And how can you force these two arrays to be of different size? In this graphic, every time when you see the red area, if you insert a 0 byte into this red area, it will happen that the arrays are of different size, and you will get the different error messages. And if you do that and build your oracle based on this knowledge, wait 12 hours and 177,000 queries later, you will end up with this. And yeah, you can't, I don't think you can read it from there, so I will. What you see here is 0002, 00 delimiter byte, 0301, TLS 1.0, and finally the PreMasterSecret hit. We're done. We have the PreMasterSecret, we can recompute the whole key material and decrypt the pre-recorded session. So this was the only implementation with different error messages that we can force. But we really would like to go further, so what can we do? Maybe we can draw conclusions on the processing time of each message. Here's our setup. We construct or prepare a special PreMasterSecret value in our attack module, send it over to a measuring machine, start a handshake with it, and after the last byte of the client key exchange message was sent, we start our measurement clock and stop it with the first byte of any response, and return the clock ticks to our attack module, apply Bleichenbacher's algorithm, adjust the logic, narrow down the interval, and finally hope to get the PreMasterSecret. So what do we find in OpenSSL? It could be that it is the random number generation. It turned out to be very hard to get the reason for the timing differences, because the OpenSSL code is a nightmare if you like to analyze it. So we couldn't really get a clue what is the real reason behind, but we think it's the random number generation, and here is why. This is the countermeasure against Bleichenbacher's attack from TLS 1.0. Only create a random PreMasterSecret if there's anything wrong with the received one, and continue with it. TLS 1.2, so you only do random number generation when there's something wrong. TLS 1.2 is aware of this fact that this may cause a timing side channel and advises this countermeasure: always create a random PreMasterSecret at the beginning, but only continue with it if there's anything wrong with the received PreMasterSecret. And OpenSSL implements the first one. So when you do time measuring, here you have the gray box is the invalid PreMasterSecret structure, and the white one is the valid one. You end up with timing differences between 1.5 and 2 microseconds. Unfortunately, there was no attack possible so far, because the timing differences were very small, and the oracle, so the SSL implementation, performs very strict checks on the PKCS #1 structure. So it's not sufficient to have 0002, but you have to have the right length, you have to have hit the right protocol version, so it's very restrictive. Another side channel is caused by exceptions. We also found this in Java, and here's why. Java, this is some pseudocode I put in. The details are not interesting. What Java does to remove the PKCS #1 structure is it simply checks, okay, if the bytes you send me are not PKCS compliant, then I will throw an exception. Otherwise, just return the unpadded text. And throwing, catching, and handling exceptions in Java is a very time-consuming task. And you can see that it's very time consuming when having a look at this. You have about timing differences of 20 microseconds. So you have this one with the invalid secret and this one with the valid secret, and you have 20 microseconds of difference. That's enough to do the attack. We used, in this case, an optimized algorithm by Bardu, 2048-bit. We had a very strong oracle, no TLS version checks, no length checks, and so on. And we used an optimized structure to speed up the algorithm. And the whole attack on a real-world network, we did it on a university network. It took 19.5 hours and 18,600 queries to the oracle to succeed. Then we found a very special behavior of hardware acceleration chips made by Cavium. You will find it in appliances of F5, of IBM. We first found it in a big IP device, then in an appliance by IBM. And the chip behaves very strange because it simply discards the first byte. No check on the first byte. You can put here whatever you like. It only checks if there's 0, 2. And additionally, you have a different timing difference of 15 microseconds. What made it really hard to apply the Bleichenbacher's attack was the discarding of the first byte, because Bleichenbacher's attack relies on the fact that there is 0, 0, 0, 2, and now you have some value 0, 2. So it was necessary to adjust Bleichenbacher's algorithm by doing some jumps in the interval narrowing. You can get the details from the paper. And this is the output of the oracle. It's very much weaker than the one we found by JSSE. And again, we did it for 2048-bit, and it took about 40 hours and 7,371 queries. And you're done. You get the PreMasterSecret of a multiple $1,000 appliance that you put into your data center to secure your network. This is the summarizing slide. You will also find this table in the paper, and it simply summarizes the efficiency and the number of queries of each of our new side channels. So, and you really did something wrong with your implementations if you get mentioned at The Simpsons. So, we have 2 minutes left.
Yes. All right, let's thank the speaker first. And questions? Everyone is stunned or sort of thinking about new defense for next year's USENIX security? Or anyone?
No questions. Seems like I did a good job.
All right. Okay. Oh, and there's one over there. Okay, state your name and affiliation.
Tom Marr, Salesforce. Is your code available to test against random other hardware implementations aside from Cavium?
It's not that you can get the whole toolkit as software. It's very specific, and you really have to adjust the whole framework for every single measurement setup. It really depends on your measurement machine, on the appliance you're trying to test. So it's not that you can do it ad hoc.
Okay, thank you.
All right.
All right, then let's thank the speaker again.